Dear colleagues, dear viewers, welcome to the meeting of the Royal Society of South Africa. Special welcome to our new member, Professor Kevin Loeb, a specialist in nuclear magnetic resonance from the Rhodes University. Welcome, Professor Loeb. And today we have a presentation by Dr. Isaac Nape on crafting quantum states of light. And this talk is co-hosted by the Academy of Sciences of South Africa. Now, let me say a couple of words about the speaker. Dr. Isaac Nape is a lecturer at the School of Physics at the University of Witwatersrand. He is focused on photonics and quantum computing. His work includes harnessing spatial patterns of light for quantum information processing and using quantum computers for solving multi-parameter problems in quantum optics. In 2024, Isaac was awarded the prestigious Mering Naude Medal for by the Royal Society of South Africa. Previous year, in 2023, he was presented with the Jubilee Silver Medal by the South African Institute of Physics. And in the same year, he was recognized as one of the top 200 young South Africans in technology and innovation by Mail and Guardian. He also serves as the Optical Emerging Leader in Optics Chair and is a Friedel Selshop Fellow at the University of Witwatersrand. Now, well, we all know that light consists of continuous waves that are described by differential equations, by Maxwell equations. And we all, well, at least I, have believed up to now that you cannot single out a single block of light, let alone molding or shaping it. But Isaac will try to convince us otherwise. Isaac, the air is yours.
Great, thank you so much. And thank you for inviting me to give this talk. So yes, I'm Dr. Isaac Nape from the School of Physics, and I'm currently working at the Structured Light Laboratory with Professor Andrew Forbes and Professor Angela Dudley, where we run a big team of talented young students and young South Africans and international people, where we try to use light as a tool for information. So basically, if you walked into our lab, you'd see a table that looks like this. We have a lot of beautiful lasers of different wavelengths and colors. And basically what we try to do is to take these laser beams and then change their spatial, their temporal, and polarization dynamics. And when you start doing that, then you go into the realm of structured light. So structured light basically just means that we take the internal degrees of freedom of light and we manipulate them in order to achieve some goal. Maybe you want to create beautiful spatial patterns, maybe you want to trap particles, or maybe you want to exchange information. We basically structure or mold features into light so that we can use them for any application that we want. And we've written many articles, but I can direct you to these two that focus on some of the things that people around the world are looking at in terms of structured light, and also unpack some of the tools that people in my field are using. So let's begin. I mean, when you start talking about light, the simplest degree of freedom or some feature about photons that you can start controlling is the polarization of light. It turns out that, well, the polarization of light, of single photons, tells us something about how the electric field of photons changes in space, okay? You can think of photons as being these oscillations that are induced in vacuum, and they are kind of directional. So in some cases, they can be planar, so they can trace out a line, or they can live in a plane, or as they propagate, they can trace out an ellipse or a circle. And so you start getting circular polarization. This circular polarization, I mean, if you created one of these laser beams and you shine it on a micro-sized particle, you'd actually find that the particle starts oscillating about its axis. And so this means that there's some angular momentum that is transferred from the laser beam into the particle. And it turns out also that, well, this circular polarization, which is associated to the spin angular momentum of light, is also directional. So you can have the light polarization vector tracing out a circle that is rotating to the right, or it can rotate to the left. And if I look at each photon that's in my laser beam that has this circular polarization, each photon has exactly 1 h bar of spin angular momentum per photon, well, plus or minus 1 h bar, depending on the handedness. And already you can see that this forms a two-level system, right? And in physics, we know that two-level systems can be represented on the Bloch sphere. Well, this is just a map that allows us to be able to describe any two-level system that can be made from combinations of maybe the right and left circular polarization. So for example, if I move to the equator of the sphere, I find that I have the horizontal and vertical and diagonal and anti-diagonal polarization states. These are actually linear combinations of the right and left circular polarization. So on the sphere, I can locate any polarization state I like. So if I choose maybe two of the opposite ends on the sphere, like the north and south pole, which have my right and left circular polarization, I can then create an encoding alphabet from this. This is because these polarization states are actually orthogonal. So that means that they are distinguishable from each other. And because of this, I can then encode information into them. So I'm going to assign the information state 0 to the right circular polarization and the information state 1 to the left circular polarization. Next, if I move to the equator, like I told you, well, I get the linear combinations. So for example, the horizontal polarization is the right plus the left circular polarization, okay? This becomes interesting because then it's saying that the polarization state or the polarization state of the photon that is encoded with this state is actually both in the 0 and the 1 state. It's not 0 or 1. And this here in quantum mechanics is usually referred to as a superposition state. We've superimposed two independent states to create another state. And this is only allowed in quantum mechanics. So now, what is the benefit of having this superposition state where I can encode two states of information into my particle simultaneously? Well, let's say that my particle was encoding information maybe about a maze, and I'd like to use this particle to solve a problem that relates to walking around inside a maze. Remember, our computers actually use transistors, which are just switches that go on and off. They're very similar to my photon that can switch between the right and left circular polarization. If I'm using my classical computer and I'm busy turning switches on and off, usually if I'm only using one switch, then I'm going to try to, encode all possible states, but one at a time. So that means if I'm encoding information about what path I'm taking inside this maze, I'm going to encode information about going through the blue path or encode information about going through the green path, but I can only do this one at a time. With quantum mechanics, I can encode two states of information simultaneously at once using the superposition principle. So, but then, I mean, with one particle, I only get two states of information, so I can only encode two paths at the same time. How do I increase the amount of information I encode? Well, let's start using two particles. So now, if I have two particles, the combinations that I have are that the two particles can both be spinning to the right, so they can be right circularly polarized, or one can be left circularly polarized while the other one is right circularly polarized. That's a second possible state I can encode. Or I can have vice versa. So my first particle is now right circular, the other one is left circular. Or I can have the case where they're both left circularly polarized. And so here you see that I have four possible states of information. And so if I relate this back to my maze problem, these states of information that I can encode into my two particles tell me something about these four different paths that I can traverse. So let's prepare our particle and then make it a superposition, okay? So a superposition of all these possible spin states looks something like this here. And so this is similar to saying that, well, I've created multiple copies of my particle, and it's actually occupying all paths simultaneously. You can imagine that, if a cat is trying to catch a laser beam, it'll be more efficient if it can traverse multiple paths at once and not just one path at a time. So this is the idea that I'm trying to reinforce here. And so while we're in a superposition, what does this mean for the maze? Well, because single photons are essentially wave functions that can be superpositions, you can think of the wave function of my superposition state as occupying all these paths simultaneously, as if I poured a bucket of water over my maze. And so if I can maybe build some technique to be able to cause this particle to then collapse onto one of the paths that lead to the exit of this maze, then I'd see that, well, my two particles at the end occupy this 0, 0 state. So from here, we use superposition to be able to go through a maze efficiently. Of course, there must be stuff that I do in between to move from occupying all the paths and then finding what path solves my problem. And so David Deutsch looked at this and, well, came up with this idea of a universal quantum computer. Okay, the fact that if we have quantum systems and we can control them, for example, if I have my photons, I can put half-wave plates in front of them, pieces of glass in the lab, which allow me to change their state, then I should be able to build logical operations that allow me to do computations. Later on, people like Grover developed algorithms that allow you to maybe use these ideas to solve the problem of finding an element that is hidden in a database. Seth Lloyd, who's quite famous in this field, also developed algorithms that allow you to maybe solve systems of linear equations. And he also came up with techniques to actually apply machine learning, but using quantum resources. So instead of training models on a GPU, you would then replace the GPU with a quantum processor that then encodes the network that you're trying to train to solve a problem. Also, there's also work where people are looking at simulating physical systems. So for example, this work here by Alberto Peruzzo, it's actually quite recent. He developed a technique to actually combine quantum computers with classical computers to be able to simulate complex molecules. So there's many, many different applications. Just to give you a feel of how these quantum algorithms tend to work, let's look at the Grover algorithm. Okay, so the algorithm that allows you to search through a database. So basically what happens is you also prepare your quantum system and then encode all possible information about the problem into the states of the system. And then what you do is you mark the element that you're looking for. And then afterwards, there's an amplification procedure that's applied to these elements, which then isolates the element that was marked and then identifies it. And I mean, a very naive way to think about it is to think of looking for a needle inside a haystack. The best thing to do is to try and make the needle look much bigger than the haystack, and there you go, you found your needle. So this is the idea that Grover had in mind when developing this algorithm. It was also demonstrated, sorry, that was a mistake. So now, I mean, I've shown you that we can use these polarized photons to actually perform algorithms such as the Deutsch-Jozsa algorithm. In fact, the one paper I showed up there was a paper where it was implemented optically using polarization states of light. Also, there's a trend now to start using single photon states for secure communication. I mean, if you can compute, it means that you can take information encoded control it or process it in some way, and then extract information from it. But this is the same goal that's achieved when you're doing, when you're trying to communicate across large distances. So Alice takes a photon, encodes information onto it, and then transmits that photon to Bob, and Bob does measurements on that photon to extract information on it. Of course, just like in quantum computing, you need a way to encode information, just like you had the zeros and ones. This is the same in communication. Here, we will use the polarization state of light to encode the information. So I'm going to use the horizontal polarization and the vertical polarization, and I'll assign 0 to the H polarization and the state 1 to the V polarization. So if Alice and Bob have access to this information basis, all they have to do is then start encoding these states into their photons. So let's say Alice maybe prepares a photon in the H polarization and then sends it to Bob. Now, Bob on his end will have a measurement device. This is a polarization beam splitter. So what it does is it looks at the polarization of the photon and then sends it to a detector, and then the detector will click. For example, since Alice sent H polarization, then this detector here will click, which records the state 0 as the information that was extracted. If now Alice encodes the state V, then Bob now collects the photon, measures it with the polarization beam splitter, and then this detector will now click. So this device here allows me to tell what information was encoded in the photon that Alice sent. Now, something strange happens when you start encoding superpositions. And now what you have to do is, let's maybe add a second basis. But we're not going to change the basis, we're just going to add another basis, and we'll call this the tilted basis. Okay, so the tilted basis constitutes of states that are linear combinations of the initial basis that I had. For example, let me take this D encoded state, so the diagonally polarized state. And if I prepare that, so Alice prepares that state, this state is actually a superposition of the H and V polarization. So it is the H and V polarization encoded in this state simultaneously. Now, if I send this photon to Bob's detector, well, because this photon is in the 0 and 1 state simultaneously, what will happen is the detectors will click will click at the 0 and at the 1 state half of the time. So what will happen is sometimes it'll click here and sometimes it'll click on the 1 state. And so if there's an eavesdropper that's trying to steal information, this will make it difficult for them to achieve that goal, because they need to know what state the photon was prepared in. So this introduces ambiguity, which allows us to have a protection of some sort against eavesdroppers. In fact, this protocol that I'm discussing here is actually called the BB84 protocol, where Alice encodes states from either one of the two bases that I showed you, so the horizontal vertical basis or the tilted basis, and Bob also randomly measures between those two bases. What happens is they only keep measurements where the preparation and measurement bases were the same. If they were not, then they discard the measurements and can actually use those signals to detect if Eve was trying to steal information in the channel. So there's two ways to achieve this protocol. You can do it using the prepare and measure approach that I showed you right now, or you can use entangled photons, where Alice and Bob now share two photons that are spatially separated but are correlated in such a way that they share correlations that cannot be explained classically. And this protocol was developed by Arthur Eckert in 1992. So basically, the quantum state that describes the two photons they share is given here. So basically, it says, if Alice measures the state H, then Bob measures the state V. Or if Alice measures the state V, then Bob measures the state H. It turns out that this state is actually producing correlations that can't be predicted by any classical system. So they're actually quantum mechanical in nature. And in fact, it was Albert Einstein who discovered these states when he was trying to show that quantum mechanics shouldn't be able to produce such correlations. However, it turns out today that we can actually produce them. So in the second case, I mean, how do you produce these types of correlations? In our lab and in many labs across the world, people use nonlinear crystals. So what happens is you have a single photon that interacts with a crystal, and this single photon has a high energy. This photon then gets absorbed by the crystal, and then two other photons are produced that have the state that I showed you before. And then these two photons can be separated and then distributed to Alice and Bob. And these two photons can then be used by them for the E91 protocol that I showed you. And so, yeah, the take-home message from this part of the talk is that we can encode information into photon spins. We can also use the spins to encode superposition states that allow photons to occupy multiple states at the same time. So there's some kind of parallelism that is built into these quantum systems. We can even entangle them, and we can also use them for quantum computing and secure communication, as I've shown you. The limitation with using polarization is that, well, photon spins are limited to a two-letter alphabet. And so this limits the amount of information that you can pack into the photons. So then what can you do? Well, just like in the maze problem, most people like to use multiple particles to try increase the information, well, the size of the encoding alphabet that they're using. So for example, you know, when we had our two particles, we ended up having 4 states of information that we could potentially encode into our photons. However, maybe this is not the best way to go, because sometimes if you add in more particles, you actually, if each particle has some noise in it, then it introduces more noise into the system. So this can be challenging. And you also find that people that try to use multi-photon states to produce these multi-photon particle encoding systems actually find it challenging to do this, because you need many or rather you need large optical tables on which you can build these types of experiments. So then it's quite resource intensive. What we try to do in our lab is to maybe look at exploring other degrees of freedom. So instead of taking photons and spinning them, maybe we can start encoding shapes into them. So these shapes are called spatial patterns of light. And for example, here I'm showing many different mode families, and they even have different types of geometries and different shapes. All of them, as you can see, are actually distinguishable from each other. So there's a way to actually tell them apart, which hints at the fact that maybe we can create an information alphabet out of them. So also, if you look at them, well, there's ones that have varying types of patterns. So at different positions locally, you have information encoded in the wave in the photon field. And so then you have some position encoding that is local in the field. You can also have cylindrical symmetry in the field. So you can encode information by encoding by using the azimuthal and radial coordinates. There's some mode families that seem to display a type of symmetry, and some of them have Cartesian symmetry. So for example, this mode here at the back and this one here in front. So there's many different mode families that you can choose from to encode information. In our lab, we also tend to play around with twisting these photons. That's also a way of giving them shapes. So for example, let me give you a beam here, which corresponds to a plane wave. Okay, this is a simple laser beam that you can find if you looked at your laser pointer on a camera. If I start twisting it, then you start seeing that it gets a vortex at the center. And if I looked at the phase front of the photon field, I'd see that it's actually twisting in space. And so this means that there's orbital angular momentum that is encoded in these fields. And so as you can see here, these twists have a handedness. I can twist the photons to the right, or I can twist them to the left. In fact, I can also increase the number of twists that I have in these photons. And so then it means that I can essentially increase the encoding alphabet using these twisted like fields. And this is because these twisted modes actually are distinguishable, or in other words, they're orthogonal to each other. And so then they form a complete basis with which I can do everything I showed you before that I was doing with polarization. But now I just have many other modes to work with. So just to show you that this is true, I mean, I can take any two of these states and I can form the sphere that I showed you before for polarization. And essentially, this means that I can also form a two-level system using these states. In general, we don't just have the twists of these photons, we also have a radial component, okay? So we can twist them, and so this gives them a twisted phase, but we can also give them rings. And so these are called radial modes. And so if we combine the twisting and the radial structure, then what we form is a large Hilbert space, which actually allows us to describe optical fields in general using this basis. In fact, this basis is a solution to the Helmholtz equation or the wave equation for photons. And so we can then use this basis to describe any optical field we want to. For example, I can take this arbitrary spatial pattern and I can write it as a superposition or a combination of those spatial modes that I showed you before. And so if I create any arbitrary pattern, it can then later be described using this spatial pattern alphabet that I've showed you. We also have that, well, you can also use the position, some people call it the pixel basis, to actually describe these optical fields. This also forms a complete Hilbert space that you can encode information with. So now you might ask me, well, beautiful, we can create nice spatial patterns. How do we create them and how do we detect them? Well, in the lab, we usually start off with a laser beam that is injected into a single mode fiber. This allows me to create that photon field that didn't have any twist in it. So it creates a Gaussian mode. Now, if I propagate this to a spatial light modulator, so this is a device that we use in our lab to actually change the properties of the field in space. Okay, if we send it to such a device and we encode this twisted like pattern here that has this spiraling phase, then the output will then be an optical field that has this shape that I desired, the shape that gives me a twisted mode. In fact, there's techniques that allow you to encode any arbitrary pattern on this device that you like. And now to detect this beam, well, what we now do is we use the reverse procedure. So we have the beam that we'd like to detect. We encode some pattern that might correspond to the beam that we want. If the beam and the pattern are actually matching, then what happens is the optical field is converted back into a Gaussian mode, which can then be coupled into a single mode fiber. And then I can count the photons that are produced by this using a single photon detector. And so this is called a match filter, okay? If the pattern that I encode on this device and the pattern that comes in don't match, then I won't get a click after I send this field to a single mode fiber. So essentially, this is a mode detector that we use in our experiments. So how do we now create entanglement? Because I showed you that we can produce our states, we can make superpositions. Maybe we want to have access to a resource such as entanglement, which we saw can be used in some of the applications that I showed you before. Well, it turns out you can use the same procedure that we use to generate polarization entanglement. And it's still the same idea. I have a nonlinear crystal that creates my two photons. And then I send the two photons onto detectors that encode those match filters that I showed you before. Now, if I change the number of twists or helical structures that I encode on these devices, and then look at the counts that I register. So for example, on the detector A, I have one that corresponds to maybe 10 twists, well, negative 10 twists, so 10 twists to the left, and maybe 10 twists to the right, then I see that I'll get a click. And everywhere else, I will not get a click. So in principle, what happens is this system allows you to generate two photons that have a total orbital angular momentum that adds to 0, okay? And so this allows you to have anti-correlations between OAM. Basically, that just means if I measure an OAM of L on one photon, then the other photon must have the opposite L. So if one photon is twisted to the right, the other photon must have an equal number of twists, but to the opposite direction. And so from this, we can then be able to have high dimensional entanglement, which can be written as a superposition that is shown here. In fact, there have been demonstrations that show that actually the correlations that are produced here are also non-classical in nature. Okay, so we can also take these entangled photons, and instead of having one photon that is spatial and the other photon also being spatial, we can start to mix these degrees of freedom. So now one photon is defined in the spatial domain and the other photon is defined in the polarization domain. This is typically referred to as hybrid entanglement. And so when you start doing this, you can then be able to shape the entanglement that the two photons actually share. So what I'm showing here in the middle is the wave function, which represents the shared quantum state that tells me what the spatial information of this photon here the spatial information of this photon here, how it controls the polarization information of its entangled twin. And once you start doing this, you can then map this wave function that combines the features of the two photons onto a sphere that looks like this here. This is called a stereographic projection. And so then all these points here have polarization vectors, which correspond to photon A, but the spatial location corresponds to that of photon B. And these are mapped onto this sphere. And if I start distorting these spheres, which is what would happen if you start distorting the entanglement in the system, either by introducing noise or by applying operations that change the states, what you're actually doing is at the level of these spheres that I've drawn here, you're distorting the texture of these states. But it turns out that while these shapes look different, they're actually topologically equivalent. And this is similar to saying that even though the states might be changing, some feature is actually maintained, and this is the topology. And where is the topology? Well, the topology here is in the number of times that these polarization states actually wrap around the sphere. But you can think of this topological invariant as counting the number of holes that determine this entangled structure. This is similar to taking a mug and then deforming it into a donut. While I changed the shape, I still didn't change the number of holes that are contained in this structure here. And so what we've been able to show is that, well, you can create these types of states, even though you distort them, these topological features can actually be retained. And this work was actually chosen to be the cover of Nature Photonics just a few months ago. So yeah, even though we can create these beautiful structures, it's very difficult to characterize them in the lab. Because remember, quantum mechanics doesn't really allow you to measure things accurately. So what we usually do is we devise techniques that allow us to intelligently extract information from these systems. So how do we do this? Well, we use a process that is called quantum state tomography. So consider this object here. I mean, I've drawn it naively as a three-dimensional shape. Ideally, we don't have three-dimensional shapes, we have quantum states, but for now, let's just use this as a toy model to describe this idea. So this shape here maybe resembles a quantum state, which I don't know. In quantum mechanics, the only thing we have access to is to projective measurements. Well, in terms of this picture, projective measurements can be thought of as shadows that I can measure on different axes. Usually, if I can get these shadows for a three-dimensional shape, there's a procedure that you can follow to recover the shape that created these shadows. Now, in quantum mechanics, well, our quantum states are produced as wave functions, and our projections are actually measurements on different quantum states. So for example, the shadows that I'm showing here are different spatial patterns that I can ask the photon, well, are you this shape? No, or are you this shape, or are you another shape? In principle, we call the type of measurements that we need positive operator valued measurements. And these are actually types of measurements that allow you to extract all the information that you need. So we do these projections, and once we are done making the projections, we then try to locate the quantum state on the parameter space that describes all possible states. If it was a two-dimensional state, then this would be trying to locate the state on the map that I showed you that tells me, well, that I can use to map out two-level systems. And if it's two particles, I can then represent the system as a density matrix, which would look something like this here. So generally, this procedure is not easy because what you have to do is, well, you can set up an equation that looks like this. Don't worry too much about the details. The idea is that you have your measurement, which I embedded inside this vector here, and you have the density matrix that produced them. And so what you want to do is to find what density matrix or underlying state produced the measurements that you observed. In other words, I want to find the state that produced the shadows that I measured. Usually you can construct a cost function that looks like this here. And once you've found the minimum of this cost function, then you've found your the solution to the problem. And so you found the state. And basically you set up this goal function and then try to find the state that you're looking for that describes your system. This in general is actually a little bit difficult because you need many measurements. So for example, if you have if you have a d-dimensional alphabet system, then you need about d to the power of 4 measurements. And I mean, this can be painful. It means if you have 10 different spatial patterns that describe the state, then you need close to 10,000 measurements to actually uncover the features of the state, which can be a painful process. So what we've been doing is I've been playing around with using quantum computers to do this. See, the cost function that I showed you before is very similar to the energy of a quantum system, which I can actually use to represent the cost function that I've encoded. This is what people do whenever they're using variational quantum eigensolvers. So you set up an energy function, and then you build a quantum circuit that you then tune to minimize this energy. Once you've minimized this energy, you can then look at all the possible distribution of states that correspond to this minimum energy. And from this, you can extract the result which correspond to the quantum state that produced your measurements. And so this is some of the work we did, and we presented it at the IBM Quantum Summit in New York late last year. And we've been trying to scale this up because it seems like it might actually work quite well at trying to solve this tomography problem. Alternatively, we've also worked on other measurement techniques. Instead of doing the 10,000 measurements that you need on a 10-dimensional state, instead what you can do is you can construct measurements that actually fit the symmetry of your problem. And we showed that we can construct superposition measurements that allow us to probe parts of the Hilbert space of the state. And then from this, we can intelligently work out what the dimensions and the purity of the state was. This doesn't reveal all the information, but it can at least tell you how many dimensions in your system can be encoded for information processing. And we actually use this to confirm the first transmission of an 11-dimensional state in a quantum experiment that resembles quantum teleportation. So the idea here is that you have a photon here that imprints information, this could be a fingerprint, into the spatial structure of your photons. This photon is sent into a measurement device that couples this photon to another distant one that is actually from an entangled pair. So here, photon B and photon C are entangled. One of the photons interacts with this photon that has the fingerprint. And through this teleportation protocol, the information is then transmitted to the other photon. And so we used my measurement technique to actually show that you can characterize the number of dimensions that you need to build your state. And why do you need this? Well, it's because this fingerprint, if I was to write it in terms of those twisted modes, I would need many, many of them to be actually able to reconstruct all the features I need in here as well as possible. And so it would be great to know how many dimensions the system has beforehand. Now, I've shown you that we can create these states, we can characterize them. Next, let's try to look at some of the applications that I promised you polarization could achieve, but was quite limited at achieving. Okay, the first one that I'll go through is quantum key distribution, which is what I showed you, where Alice and Bob were using polarization states to exchange information. Using the measurement devices that I showed you, you can actually repeat the same procedure, but now using a larger encoding alphabet. So on this side here, I have the prepare and measure protocol. So Alice and Bob can choose maybe 3 of these patterns to encode information in. I mean, this is still larger than the 2-dimensional polarization states that I showed you before. So now we have access to a 3-letter alphabet. So they form their logical bases and their tilted bases, which we use to confuse the eavesdropper. And following the procedure that I showed you with polarization, they can then start to, Alice can randomly choose different spatial patterns to encode information with, while Bob chooses different bases or any one of these 2 bases to do the measurements with. And following the same procedure as before, they can then create a sifted key that they can use to encrypt information. This here is more beneficial because I have a larger alphabet that I can use to encode information and not just 2 states of information. So we've written a nice tutorial article that shows how you can do this using a prepare and measure protocol and also an entanglement-based protocol where Alice and Bob share entangled particles to do this protocol. Also, we've been able to demonstrate that you can actually, instead of just sharing these encryption keys or information between Alice and Bob, you can actually distribute the information between multiple participants. So for example, here, I'm showing these 5 locations at which maybe 3 different participants are located. Each of them actually has a segment of an encryption key. And so we've shown that using these spatial patterns, it's actually possible to distribute encryption keys amongst multiple participants, but using spatial patterns of light. In fact, I think we still hold the world record. Initially, people used polarization states to do this. This protocol is actually called quantum secret sharing. Next, well, I've shown you that we can do computing with polarization states of light. Can we still maybe also do this using spatial modes? And it turns out, yes, we can. We can structure photons to do computing. So how do we do this? Well, if I create a laser beam and then I send it onto those spatial light modulators that I showed you that allow me to control the spatial distribution of light at every location in space, I can essentially encode a vector. So a vector can be like a multi-element object that encodes multiple numbers in it. I mean, these numbers can maybe be pixels inside an image. It could be a quantum state. It could be anything, right? So I encode my photon with such a vector using a spatial light modulator, and then I can send it to a second spatial light modulator that allows me to embed a matrix inside it. So matrices allow me to actually operate on vectors, okay? So for example, when this field here propagates and encodes the vector that I want, after it interacts with the second spatial light modulator, I can achieve matrix multiplication. Okay, if you're a mathematician, matrix multiplication allows you to take a matrix and each row inside this matrix is multiplied as a dot product to these elements in here. And then at the end, you can read out this vector as an output. Why is this essential? Well, quantum mechanics can be performed using matrix algebra. And so, for example, this vector that I've encoded is actually encoding the equivalent of 2 qubits or 2 particles that are encoded with the plus and minus state. And the matrix here actually encodes an operator that can act on the on the matrix or the qubit state that I've encoded. And the output would be the action of the operator that I've encoded acting on the state and then giving me this result as an output. Equivalently, I mean, this can be treated as a platform for doing things such as machine learning, where, for example, this vector that I've encoded is actually encoding feature vectors, and the second one encode maybe convolution layers or parts of the network that I'm interested in, and then the output layer then gives out the result. For example, if I'm trying to do machine learning, like for example, trying to identify cats from dogs, then this system here, the output would be able to tell me if the optical field had a cat or a dog encoded in it. So recognizing this, the fact that you can use this for many different applications, we started looking at using this to emulate quantum computing, as I have told you. And the idea here is that, well, you can encode information into these specialized modulators that actually looks something like quantum computing. And so through these procedures, you should be able to demonstrate quantum algorithms. In fact, in this article, we demonstrated an algorithm which is called the Deutsch-Jozsa algorithm, which allows you to identify even or odd functions. Another thing we've looked at is in quantum computing, there's an algorithm which is called the variational quantum eigensolver. That was basically the tool that I used to solve my tomography problem. And the idea is that you have a quantum state, and then you have a dynamic unitary, people usually refer to them as dynamic ansatz, an ansatz circuit, which you then use to actually scan through all possible solutions that solve your problem. Motivated by this, we actually took our optical matrix multiplication architecture that I showed you from before, and we showed that, well, on one SLM, you can spatialized modulator, you can encode information about a state that is unknown. Say, for example, I had my photon field and it interacted with maybe turbulence, which could destroy the spatial structure. We can then use this architecture to actually learn what the turbulence did to the photon. And so we can then use a second SLM to dynamically minimize a cost function that allows us to identify when this SLM has imprinted information that is encoded on the first SLM. And so from this, you can actually start using this variational quantum computing architecture to actually solve different problems in optics. For example, what I've stated is usually referred to as adaptive optics. You can use this also for quantum imaging. And we've been playing around with looking at other applications in the lab. In fact, this paper just got accepted at Optics Express. So this is an example of the phases that are encoded on each of these pixels here. Over time, the system actually learns what those phases are and is then able to actually recover the information that was encoded on the first SLM. In principle, we shouldn't know what's on the first SLM. So yeah, in general, you could treat SLM1 as a black box, and our system should be able to iteratively learn what's encoded on the first one. With that, I'd like to thank you all for your attention. And I'd like to also acknowledge most of the people that are actively participating in the research that we're doing. And also I'd like to acknowledge a lot of our funders and collaborators. And yeah, thank you so much. And I'm open to questions.
Thank you very much, Isaac. It was quite mind-twisting. Anyway, are there any questions? Not yet. Well, then in the meantime, let me ask you something. Well, first of all, what I wanted to ask you is this. If so your photon behaves basically as an electron with spin up or down. Is that right?
Yeah.
Okay, so if there are only two directions for the spin, up or down, you have a system with 2 degrees of freedom. You have a binary system. But
Yeah.
despite that, you drew columns consisting of 4 elements. So where do these 4 coordinates, 4 elements come from?
For when I showed the matrix, I just want to recall.
Even earlier than that.
So
Even earlier than that, you started talking about.
so
Yeah, even earlier than that.
four column in so
4 component vectors. Well, the spin should.
okay. I see. Yeah, so in this specific example, I think I know exactly what you're talking about. So the idea is that, a two-level system.
Yeah. Here you are. You're right at the bottom. Yeah.
Yeah. So what I've done here is, you see, each particle can be in either one state or the other. So then there's 2 possible states, right? In vector notation, this corresponds to a 2-element vector. This is just for one particle. Now, if I have 2 particles, then I need to have a 4-element vector. I mean, mathematically, we usually say that we take tensor products of the vector spaces of each individual particle. So if one particle gives me 2 elements, another particle gives me 2, the product of the 2 is 4. So then to describe this vector, I have 4 elements, right?
But where do 2 particles come from? Don't you have just one photon?
Oh, here, what I've done is I'm now using 2 particles. Because remember, I was like, if I only have one particle, then the one particle can only encode 2 states of information, right? About maybe path A or path B. If I have 2 particles, then I have 4 states of information.
Okay, but these 2 particles, aren't they separate? How?
Yeah,
They don't form a pair. They are separate in space.
Yeah, so these can be 2 independent particles that I've created. I could create them using that nonlinear crystal that I showed you before, right? You can create them and then turn them into a separable state, and then map them onto this superposition state that I've shown you here.
So despite the fact that they are separate in space, you can read the information from the 2 particles simultaneously.
Precisely.
You know how to correlate these 2 particles, yeah?
Yeah, I mean, over here, I don't really care too much about the correlations. I just care about being able to encode all the possible states that I want into them, right? But yeah, usually in these algorithms that would map the superposition onto the solution, then you do care about the correlations because there might be entangling operations that are performed.
Okay, well, thanks
Yeah.
very much for that.
Yeah.
Are there any other questions?
I think I see comments in the chat.
Okay, let's have a look.
Oh.
No, those are technical. Okay, now while we still have a couple of minutes, one more thing.
Yeah.
You have spin, well, something like a spin, but that is actually a polarization, right?
Yeah.
But it behaves as a spin. And you also mentioned the angular momentum. Now, what is the difference between the spin and angular momentum?
So that's a great question. So light in general has angular momentum, and you can decompose the angular momentum into spin angular momentum and orbital angular momentum. So then the spin angular momentum would be associated with the intrinsic spin of the photons, whereas the orbital angular momentum would be associated with the extrinsic spin. So it's coordinate dependent, whereas the spin angular momentum is not. And I mean, so there's many different experiments that also show you the difference, you know. So like I showed you with I think I made an example somewhere showing that if you send a circularly polarized beam, so a beam that has spin angular momentum, then you can cause a particle to rotate on its axis. Now, if you send a beam that has orbital angular momentum, then you find that actually the particle now starts circulating in an orbit. You know, it has this orbit-like motion.
I see.
Yeah.
Okay.
Yeah.
Well, one more thing is you mentioned when you spoke about the Bloch sphere, you said that any two-level system can be represented by a point or by a trajectory on that Bloch sphere. Why is that so? Why is there such a correspondence between a two-level system and a sphere always? Why is that so?
That's a very good question. I mean, the Bloch sphere is usually used to represent spinors, right? And we know that spinors can be described using the SU2 group. I mean, it's very complicated, but the idea is that you can link things that have physical rotations with things that can be parameterized on spheres, okay? So for example, you know, I usually talk to the students and tell them, if I have maybe a spin up particle, so right circular, I can associate with spin up. Now, to rotate that to a spin down particle, I need to rotate my hand by 180 degrees physically, right? So on the sphere, that's similar to moving by 180 degrees from this, from the North Pole here to the South Pole. And so these are actually also orthogonal to each other. And so the symmetry is also built in that way, that like orthogonal states are always on opposite ends on this sphere.
I see.
I mean, also another reason is, I mean, quantum states are normalized because probabilities add up to 1. And mathematically, if you write it down, the equation that you write to actually represent this looks like an equation that describes a point on the surface of a sphere.
Okay. If there are any other questions? If not, well, Isaac, thank you so much. It was extremely well presented, and your pictures actually make things much, much clearer. Sandra, before Sandra wants to say something, but I have not forgotten. I need to announce the next talk. We look forward to the talk by David Dodu Aren, Professor of Materials Science and Engineering from the Institute of Applied Science and Technology in Ghana, and that will be on the 16th of October. And if I understand correctly, Sandra, we still don't have the title, so the title is to be announced in due course. Am I right?
Yes, I'm afraid so, Igor. He seems to be traveling a lot. Haven't been able to get hold of him.
Okay.
This was really a brilliant talk, and I mean, I didn't understand much of it at all because it's not really my field, but incredibly, very, very well presented. Thank you, Isaac.
Isaac, thanks very much one more time, and thank you everybody for attending, and we will see